thanks a lot for the opportunity to present some of our recent work we achieved in petros, which is another Horizon 2020 project. And I would like to just very quickly start. Now I need, well, to give you an overview about aim and vision of our project, which is also very similar to SmartNanoTox. So we would like to establish some new tools which we can use for hazard assessment, but our focus is more on adverse effects caused by a long-term and low dose exposure of occupationally relevant nanomaterials for human and the environmental system. We also use very similar materials which Tobias just showed, and we even focus a little bit more on materials from which we have some data for long-term effects in animals, so that we can do a better in vitro and vivo correlation for these endpoints. So how do we do this? Of course, we also use many in vitro system, ecotoxicity models. We use the knowledge you generated in SmartNanoTox for the AOPs to define the bioassays which we use to investigate the effects. And of course, we will also try to correlate this with in silico modeling approaches. So this is a brief overview about the different work packages we have in petros. As said, we focus on nanomaterials from which we have data, in vivo data, and for which materials we know that they induce long-term effects. Then we have 3 work packages focusing on lung, intestine, liver, and ecological models. And one of our just recently started task is also to do some laboratory round-robin tests to see how reproducible the assays are that we develop. And as said, we closely correlate or try to collaborate with a work package which is focusing more on the in silico tools for predictive risk modeling. Yeah, and of course, everybody who knows me assumes that I'm responsible for the lung models in this European project. I just briefly show all the partners that are involved in this work package. I do not have time to introduce them all, and I would really like to acknowledge the great collaboration and input they give me for all the presentations. I will also share some of results from other partners here in my presentation. So the main topic of my talk is that I would like to share some thoughts and results about in vitro tests which we can use to predict lung fibrosis. You have already heard about lung fibrosis, but I think before we start to look into in vitro tests, it's really important to think about the pathogenesis in situ, in humans and in animals, and how this is diagnosed. So in this histology picture, you see a healthy lung, alveolar region. These are mainly air-filled compartments separated here by the interalveolar septa. It's a very thin barrier, which is important for sufficient gas exchange. So when you have now a fibrotic tissue, this is from a mouse lung, you see that the picture completely changed. You have very thick walls, and you can assume that oxygen diffusion is not optimal anymore. And indeed, in medicine, fibrosis is defined as this accumulation of connective tissue, which you have seen in the histology picture, and it's in and around an inflamed tissue, which can lead to scar formation and, of course, ultimately to death. So this is a very long-term event in humans. It can take 20-30 years, in animals several months. And it's also important to look briefly into the cells which are the main key cells which are relevant for the development of fibrosis. So we have already heard about macrophages, which are mainly located at the apical side of the alveolar barrier. If they start to induce an inflammation, and maybe we heard from Tobias that they are not responsive for all the materials, then they also mediate the response with the alveolar cells, which are type 1 and type 2 cells, and in the presence of many cytokines, chemokines. Among these, we have tumor growth factor beta, which is very important. The cells start to transit from an epithelial phenotype into a mesenchymal phenotype, and you also see that there is an excessive accumulation of fibroblasts in the connective tissue, which is that the fibroblasts are activated by tumor growth factor beta. They proliferate and they release collagen and fibronectin and other fibers into the extracellular matrix. So all this then results in this scar formation in the connective tissue. You have already seen this picture many times, but I think if it makes sense to briefly go over all the events, because this will also then explain how we have set up our in vitro assay. So this interaction with the cells is of course very important. For this, maybe it's more relevant to use macrophages and alveolar cells, as the fibroblasts are below the apical side. So this already indicates which cells you should use to test this interaction. Then we have seen in this acute response, which is characteristic with this inflammatory and profibrotic mediator release. This can induce then a recruitment of pro-inflammatory cells from the bloodstream. We have a chronic inflammation, which can also induce a loss of the barrier integrity. We have other immune cells that are activated. Finally, we see this fibroblast, myofibroblast proliferation, which are responsible for the extracellular matrix deposition. Again, the time factor is important, so we cannot really expect an acute extracellular matrix deposition in a 24-hour assay. And so if we look at short-term acute exposure, maybe we focus on these endpoints. And if we have repeated long-term assays, then we can hopefully look in other endpoints which are more at the end towards the adverse outcome. And these are all factors now which are relevant for the choice of our lung cell models, because this also is indicative for the endpoints we choose. And I think I will show you some examples of assays which we use to address these different key events. Then another very important consideration are, of course, the lung cell types. I have just mentioned 3 of them, which are the macrophages, fibroblasts, and, well, actually 4. It's alveolar epithelial type 1 and type 2 cells. So these are cells which we should try to include in our in vitro assays, as they are the relevant cell types in the fibrosis adverse outcome. We also have to think about which materials which we use to establish our assays. And of course, you have all heard about carbon nanotubes, which can induce an inflammatory response in humans. This is a study done by Anna Shvedova. There are many review articles who summarize the induction of pulmonary fibrosis for many particles, not only nanoparticles, but also bigger particles. And also in animals, a fibrotic response has been shown upon exposure to carbon nanotubes. It's not only the material which is relevant, but it's also the concentration we use. And as we would like to mimic more the occupational exposure, we should try to avoid very high acute exposures, but more we more aim for a repeated exposure to very low concentrations. And this should be in the range, in a total range of 12 to 46 micrometer per square centimeter, which has proposed already some years ago by Gangwal and colleagues, who modeled in combination with experimental data the full working lifetime exposure to a realistic carbon nanotube aerosol concentration. So our assays should not go, or should be responsive if we expose them to this concentration in order to avoid overload situation. Let me briefly start with a slide to show you a slide from collaborators in PetWars, which is Dominique Liaison and Sibyl van der Brühl. They have already published some years ago fibroblast in vitro assays to predict the onset of fibrotic response upon exposure to carbon nanotubes. So they have used monoculture assay with fibroblasts in submerged conditions. They looked at proliferation, differentiation, and collagen production, which I mentioned before, which are very important key events to predict fibrosis. Here are some results. You see here positive controls. They induced all the three markers which I just mentioned: increased proliferation, differentiation, and collagen production. However, if they expose it to carbon nanotubes, they only have seen a significant increase for the proliferation. And this is also correlated to the same material, to the same nanomaterials which they used in an in vivo assay. So they concluded that their fibroblast in vitro test is predictive to reflect the proliferative activity upon exposure to carbon nanotubes. And something which they also have shown is that this proliferation activity depends, of course, on the physicochemical characteristics of the materials. So we have actually started, this is a work we started in 2005, which has been supported by PETA International Science Consortium and MATEC Corporation. They have started to establish a co-culture model with epithelial type 1 cells, primary cells from human donors, which they combined with fibroblasts and endothelial cells on the lower side of the membrane insert. Here you see a histology image of these cell cultures, and the great advantage of this system is that they are stable, that this EpiAlveolar lung node is stable at the air-liquid interface for several weeks, which was really one of the key points for our fibrosis work. So they shipped then the cultures to us, so from the US to Switzerland, and when we received the cultures, we keep them in the incubator for some days to relax a little bit, and then we have added monocyte-derived macrophages, as we assumed that this is a relevant cell type to be included in our assays. So first we did, of course, a lot of controls just with some positive mediators like tumor growth factor beta to see if the model is stable at the air-liquid interface for several weeks. We used it over 3 weeks, so 21 days, and exposed them to TGF-beta. And you see, in comparison to the control, you see we have observed a thickening of this extracellular matrix. And this was very characteristic then in the histology images, that we have seen a retraction and this module formation in the image. So the next step in our lab was then to expose these cell cultures to an aerosol, which was done by aerosolization of a well-defined nanomaterial dispersion using the cloud system, which is commercially available by vitro. So we have used the NanoGenoTox protocol to disperse the nanomaterials, and of course you are well aware that with this integrated quartz microbalance in the system, it's very nice that you can online measure the deposition of the nanomaterials, which is a very important information to make the prediction about the dose-dependent responses you will get. So as said, we tried to use relevant nanomaterials to establish the model, or to work with the model. And for this we have used silica quartz TQ12, which is a particulate positive control, and we use 2 carbon nanotubes, nanoSil, which is a thinner, more tangled form, and the Mitsui 7, which you also have used in your projects. So what we did then, so we did 1 exposure with the cloud system. We could measure the deposition, and then we exposed our EpiAlveolar model every day over 3 weeks during the working days. So this resulted in a total of 15 repeated exposures, here. And you also see the range of deposition here, which was measured via the quartz microbalance. So you see with it needed some optimization, of course, for the stock solution. And then we did also different dose ranges, but this is just an example to show you that we are in the range of this full work lifetime exposure, which has been recommended by others. So we then started to look at the interaction of the carbon nanotubes with the cell membranes in the EpiAlveolar model. And here you see some enhanced dark field images, which show DQ12, nanoSil, and Mitsui in the cells. So it was a little bit tricky to prepare the cells for this microscopy method. We had, because the filter insert gives a lot of background information, so we had to detach the cells from the membrane, and then we just had a suspension of cells which we could spin down on a cover glass. So we cannot say which cell type we see, but we just see that the material interacted with cells, that the material is inside the cells but also attached to the outer cell membrane. Then the next step was, of course, to assess some pro-inflammatory and pro-fibrotic mediators. You see here the graphs for TNF-alpha and TGF-beta release, for DQ12, nanoSil, and Mitsui. What is very interesting is that some of the responses only occurred later, so after 2 weeks or 3 weeks, and the response was also very moderate. We saw significances, but it was not as high as expected. And this is also in agreement with what Tobias said, that macrophages might also be able to counteract with anti-inflammatory cytokines. So this is something we still need to investigate a little bit more. So the next step, or one of the assays we also used, was of course the measurement of the membrane integrity, which was even a little bit more difficult, because you see already here for the untreated cells, we had huge standard deviations. The cells looked all good, but the device, we had this millipore device, it's also, you have also for each person who is using this system, you have some variability. However, for the positive control TGF-beta, we saw quite a decrease in tier values, and for the materials, we have some indications that there is a loss of the barrier function, but it was not significant. Then, of course, finally, we looked into the extracellular matrix deposition. We have measured cytokine release, but I just show you here some confocal images. These are Z projections for control DQ12 and Mitsui exposed cells. And it's clearly visible that for Mitsui 7 exposed cells and also for DQ12, you have a thickening of the membrane. We also did some fibroblast measure or staining, and we see some increase in fibroblasts, but we were not able to quantify. Also something which we need to do in further assays. So what we could conclude based on these experiments and results was that we can use this EpiAlveolar model to predict inflammatory and fibrotic responses in the presence or exposed to carbon nanotubes and DQ12. And we currently also look now into other materials like titanium dioxide and cerium dioxide. And again, I think the time factor is really important, as we have seen many responses like collagen release, fibronectin release, thickening of the membrane only after 2 or 3 weeks in culture. I would also like to share some unpublished data with you, just to show what else we do in petros to enhance the physiological relevance of our models. And one is, of course, to introduce breathing conditions, which is done by our collaboration partners at the University of Pisa, Arti Aluvalia and Roberta Nossa, who helped or who established this DALI bioreactor, which can simulate flow and the breathing by including a dynamic membrane. Let me show this here in this scheme to make it more clear. So we have one chamber where we have air flow. In the lower compartment, we have medium flow, and in between, we have a porous membrane. And this porous membrane is made of bionate, and it took them quite some time to optimize the membrane, because you can imagine it has to be flexible, it has to be thin, and it has to be biocompatible, and sometimes this is very difficult to combine. So in the meantime, they have optimized the membrane production. We use it now in our lab to do some first growth tests. We use A509 cells, which represent human alveolar epithelial type 2 cells, and we also started with healthy cells. And here I just show you briefly the briefing, how this it is introduced by air pressure, by a changing air pressure, and you can very nicely mimic the same frequency and strength of the alveolar breathing mechanism. So current experiments in my lab are ongoing to test the cell behavior under these breathing conditions. Another possibility to increase the physiological relevance is to use this the aerosolization of the powder, and I have shown you the cloud system which needs a dispersion. So we have to disperse the powder, we have to characterize the dispersion, and this can be overcome by a direct exposure system for powders. It's established now in the lab of Vicky Stone and David Brown at Heriot-Watt University. And they have already tested the aerosolization of various nanomaterials from petros. And you see that it's possible. You can achieve a very homogeneous deposition pattern of powders. It's always aggregated, but this is the same characteristic as for the pristine material. So with that, I would like to conclude and still really force a lot that we try to predict, and we always need to consider, we think it will happen also in the mouse lung or in human lungs if we use the same materials. And we need really a combination of different techniques, acute exposure, chronic exposure. We need animal experiments to really get the complete picture. So for the epithelial tissue models we use and we further optimize, it's very important to have the structural functional characterization also over long term. And then the AOP concept really helps us to choose relevant assays for the endpoints which you all recommend us to use. And then we also need to include positive controls, particle controls and assay controls to show that the system is responsive. We need the dosimetry aspect, which you have heard much more from Ottmar Schmid. And of course, we need to show that it's not only reproducible and usable in one lab, but it's also that you also can transfer the know-how to other labs, that they can reproduce it. And this is very important then also for the standardization and approval procedure for alternative test models. So with that, I would like to acknowledge my group, and especially Hanna Barosova, who did all the work with the EpiAlveolar model, which I presented. And of course, I would like to acknowledge Petros and all the partners and you for your attention.